Welcome to The Explainer. Today, we are diving into something pretty ambitious. We're going to explore exactly how we take the beautifully chaotic physical reality that surrounds us every single day and somehow transform it into the strict, structured, highly logical universe of Java programming. It is a completely fascinating process, and honestly, it's one that completely revolutionized how modern software is built. So I want to kick things off with a bit of a philosophical question for you. How do you actually teach a computer to understand the real world? Think about it for a second. As humans, we naturally perceive the world in terms of objects, right? We see cars accelerating, dogs barking, maybe a towel absorbing water. We definitely don't see a sequence of abstract mathematical functions. We see distinct entities that have specific attributes and specific behaviors. So how on earth do we get a machine to think like that?
Well, to answer that, here is our roadmap for today. We'll start with the programming paradigm shift, then cover the birth of Java, its essential building blocks, controlling the flow, and finally, classes, objects, and blueprints.
Let's jump right into Section 1, the programming paradigm shift, from chaos to objects.
To really appreciate Java, we kind of have to travel back to the old school days of procedure-oriented programming. Imagine a world where software was just this linear series of steps acting on data. As programs grew larger, the code got far too complex and chaotic to manage. It was literally like leaving your cache on a table for anyone to grab. That is exactly how older procedural languages treated global data. Object-oriented programming, or OOP, completely flips the script. It acts way more like a bank vault. It organizes a program around its data by bundling the data and the methods together into objects, granting really strict control over who gets access. So in this setup, the data actually controls access to the code.
Take a look at this. Instead of a messy web of global data, notice how Object A, Object B, and Object C are all functioning independently. They communicate securely by sending messages to one another through well-defined methods. Think of it like your bank account. A customer object sends a message to an account object to decrease its balance. It's clean, it's organized, and most importantly, it is secure.
And that brings us to this absolutely crucial concept, encapsulation. It's basically the mechanism of wrapping those attributes and behaviors into a single object and then completely hiding the complex implementation details from the outside world. You don't need to know the physics of how fuel injection works just to press a car's gas pedal and make it go. That kind of information hiding is the absolute bedrock of good, reliable software engineering.
Okay, Section 2, the birth of Java, a platform-independent revolution.
So now that we understand that massive shift to objects, let's time travel to the early 1990s. The internet was just appearing on the horizon, and the programming world desperately needed something new. In 1991, James Gosling and his team at Sun Microsystems were dealing with a massive headache. Languages like C++ required these really expensive, full compilers that were targeted for very specific CPUs. They needed a language that was truly portable and architecture neutral. Well, 18 months later, they had a working prototype named Oak, and by the spring of 1995, it was publicly announced to the world as Java.
If you want to understand why Java literally took over the world, you really just have to look at these buzzwords right here. It was designed from a totally blank slate to be simple and naturally object-oriented. It's robust, meaning it handles errors incredibly well without crashing. It's multi-threaded, which allows programs to do a bunch of different things at once smoothly. But the real game changer? It was architecture neutral and portable. Write once, run anywhere. That specific feature is what made Java an internet-scale powerhouse that is running on billions of devices as we speak.
Let's move to Section 3, Java's essential building blocks, the grammar of code.
Let's actually look under the hood now. If Java is a spoken language, these are the fundamental alphabet and grammar rules it uses to store and manipulate basic info. Java defines 8 simple elemental types of data. 4 of them are dedicated entirely to integers or whole numbers. Now, instead of a one-size-fits-all approach, Java smartly categorizes these whole numbers by size to optimize memory. It goes from the tiny 8-bit byte to the short to the incredibly common 32-bit int, all the way up to the massive 64-bit long, which you'd use for calculating, say, astronomical distances. Rounding out our basic vocabulary, we have our fractional numbers, which are represented by float and the highly precise double. We also have char for storing characters, and impressively, it uses Unicode, meaning it can represent international symbols from all over the world, not just the basic English alphabet. And finally, we have Booleans, which simply act as a little on-off switch storing true or false. These right here are the raw materials you use to write robust expressions.
Now, what's genuinely fascinating is what Java does with these building blocks when you're done with them. In older languages, programmers had to manually allocate and free up memory, which, let me tell you, led to some disastrous bugs. Java fixed this by introducing garbage collection. It automatically hunts down objects with no existing references, destroys them, and reclaims their memory. This was a massive win for developers and directly contributes to that robust buzzword we saw a minute ago.
Section 4. Controlling the flow, directing the logic.
Having established our building blocks, we get to act as the directors of the program. We dictate the exact logical paths the code takes based on specific conditions. A really fantastic example of this is the for loop, which repeatedly executes a block of instructions. It runs in this beautifully logical 1, 2, 3 sequence. First, initialization. You set a starting loop counter. Second, the condition. The program tests if a target value is met. If it's true, it runs the code. And third, the iteration. It increments or decrements the counter and just starts the test all over again. It totally demystifies how computers can do repetitive tasks so unbelievably fast.
And beyond loops, we have a whole squad of other crucial tools acting as the traffic cops of our Java program. We've got if-else statements for simple forks in the road, we have switch statements for when a program has multiple distinct paths to choose from, there are while loops that just keep running as long as a condition remains true, and jump statements like break and return if you need to immediately hit the brakes and exit a flow.
Finally, Section 5. Classes, Objects, and Blueprints. Modeling Reality. This brings us to the culmination of our explainer. We're going to tie all of this syntax and grammar back to our initial, super ambitious goal, modeling physical reality. Let's see how this builds into arguably the most important concept in Java, the relationship between a class and an object. You can think of a class as a blueprint for a house. The blueprint itself isn't a house, right? You can't live in it. It just defines the attributes and the behaviors. The object, however, is the actual physical house built from that blueprint. And the real beauty here is that you can build many unique house objects from that one single blueprint class.
Now, to manage the complexity of all these blueprints, we use hierarchical classifications. It honestly looks just like a high school biology chart. At the very top, we have a really broad material object. As we filter down, it gets more and more specific: animal, mammal, human, shopkeeper, florist, until finally we reach a specific, unique object at the bottom, like Flora the florist.
This chart works seamlessly because of a concept called inheritance. Flora doesn't just have the attributes of a florist. She automatically inherits traits from being a shopkeeper, from being human, and from being a mammal. By deriving a subclass from a superclass, objects inherit traits from their parent categories. This makes complex code incredibly structured and highly reusable. You write the human traits exactly once, and every human subclass gets them automatically. It's brilliant. Which leaves me with this final thought for you to chew on. When we write Java code, when we meticulously map out our reality into these intricate class hierarchies and carefully defined inherited attributes, are we really just programming computers? Or are we actually reverse engineering and mapping out how we, as human beings, perceive and categorize the physical world itself? It makes object-oriented programming not just a technical coding tool, but a truly fascinating philosophical exercise. Thank you so much for exploring this with me today.